So the A, B, and C with these position vectors are three vertices on a cube, and we're asked to find the volume of the cube. So at the moment, we've just got the vectors from a fixed point, the origin, but we can work out some of the lengths on the cube by subtracting them. Because what I mean is if we've got O going to A, and we've also got O going to B, then we could work out this vector here, which will be a length on the cube. Now the thing is, at the moment, we don't know whether it's going to be a short length here, or it's going to be a diagonal, because that would be possible. Or a third option would be that it could be the space diagonal, so a longer diagonal, not just between faces, but across the whole cube. So this is something we can investigate, but what it's going to involve is some subtractions. So this is A and this is B, which means that AB is going to be B minus A. It doesn't really matter what way we subtract them, so I'll just go with that like I've started it. So B minus A is going to be 8, 5 minus minus 3, minus 2 minus 1, minus 3, 9 minus 5. And what we can do now is work out the length using some Pythagoras. So 3D Pythagoras, we just do 8 squared plus minus 3 squared plus 5 squared, square rooted. 34, 94, so this is root 98. I could write that actually as 2 times 49, so 7 root 2 if I wanted to. Okay, and let's proceed in a very similar way so with the others. So C minus A, that's going to be, let me just grab these and bring them down. Okay, so 8 minus minus 3, so 11, minus 5, and minus 1. So therefore AC is going to equal 121 plus 25 plus 1 square rooted. That is 26 plus 121, 147 square rooted. In fact, 3 goes into this because 3 goes into 1 plus 4 plus 7, but 9 doesn't. I think I'll just leave it like that for the moment. And then C minus B. 3 minus 2 minus 6. So BC equals 9 plus 4 plus 36 square rooted, which equals the square root of 49, which equals 7. Now, I was talking about some of the lengths at the start. This, like root 49 is clearly the smallest out of all of them. It's got to be the side length. And then the next biggest is the root 98, so that's going to be a diagonal. And then that means that this is going to be the space diagonal. So if I draw a little sketch of the cube now, I could put, we had AC as a space diagonal, so maybe A is here and then C is here. And then it was BC, so B would go here because BC was the short length and then AB was the diagonal. So that's what it could look like with O perhaps over here somewhere. But back to the volume. So the side length is going to be 7, therefore the volume is 7 cubed, which is 243. Next up, we've got a second cube, and this time we're given some of the vectors, not the position vectors, but the vectors PQ and PR. So I'm going to draw a little diagram. Let's say this is the origin. Diagrams are often very useful for vector questions. So we've got OP, and let me put Q over here. And then PQ will be this one. And then I'll just put R over here. It's not, necessarily accurate. And then PR is this one. So what we can do here is look at the scalar or dot product. PR times PQ times cos of the angle in between them, so cos 60, will equal the dot product between the two vectors. I'm not going to, that's like essentially well, not a definition of the dot product, but you can show where it comes from. But we're just gonna go with it. Let me just write it. So A dot B equals AB cos theta. That's what I've used here. So now we need to work out each of these. PR, the length is going to be 7 squared, or 49, plus 1 plus 0 square rooted, so root 50. PQ, 3 squared plus 4 squared plus alpha squared, square rooted. So 25 plus alpha squared. Cos 60, that's an exact value to learn. That is going to be a half. Equals, and now we can do the dot product. So 3 times 7, 21, plus 4 times 1, 4, and then there is no alpha. So this is 25, times it by 2, we get root 50 times 25 plus alpha squared is equal to 50. This means that root 25 plus alpha squared is 50 divided by root 50, which is simply root 50, which means 25 plus alpha squared is going to equal 50. Therefore, alpha squared is 25 and alpha is 5. Remember, we were told that it was a positive constant, so I can ignore the negative. Great. Finally, we're asked to find the length of the diagonal on this second cube. So let's have a think about this. I didn't go into details before, but if we draw the cube, then although I drew a sketch before, we've got the angle between P, R, and Q to be 60 degrees. And the only way that this can be the case is if they're all diagonals. Because what we would then create is an equilateral triangle inside the cube. So to be honest, when I did it, I didn't see that straight away. I decided to try and work out what RQ was. So I did PQ minus PR, which is the position vector Q minus P, minus R minus P, which becomes Q minus R, which is then RQ. And I subtracted these and got as my answer minus 4, 3, 25, and then RQ was again root 50. And that is actually what convinced me that it was an equilateral triangle, but the 60 degrees should have given it away, I'm just trying to say. But if you don't see it, you can still get the other other means. Okay, so actually what we can do is we could just maybe look at this triangle and we can see that we've got QR and then this is root 50. Let's call the side length x. So 2x x squared plus x squared is root 50 squared. So 2x squared is 50. X squared is 25. So x is 5 here, which means if I want the, I think they called it the space diagonal here, length of a diagonal of the second cube. Okay, they mean the space diagonal, the longest diagonal. I feel like that's a little bit confusing because the ones we've been dealing with before have been diagonals. So space diagonal is going to be 5 squared plus 5 squared plus 5 squared square rooted using 3D Pythagoras, which is root 75 or 5 root 3. All right, well done.